Parent function is the simplest version of a function with no transformations done to it. So we're starting here with y equals x, and it's a simple linear equation. And one of the things that we're going to do to this is we can do a vertical shift up or down. And it's kind of confusing if you think about it. If I was to shift this down, it's going to appear that it's also that all I did was shift it to the right because the line goes on forever and ever. So let's add another line here. And this time what I'm going to do is y equals x plus 1. And what I see is that this is a vertical shift up 1, but it might also look as if I had shifted it to the left 1 space. And notice that the scale on here, 0, 1 is here, 2, 3, 4. So it's counting by 2s on the scale. So I've shifted this up 1. And also, let's do another one where this time I'm going to have y equals x minus 2. So this time what I've done is I've shifted it down 2. So the parent function is y equals x. And what I also have is in this family of functions, I have plus 1 and minus 2. So when I do this vertical or horizontal shifting, that's also called a translation, is where the line is moved. The next type of transformation is a rotation. And in the case of this linear equation, what I've done is I've rotated it 90 degrees. And yes, this is a 90-degree angle here, but also look at it from the x and y axis standpoint. If I was to turn the entire graph, then my y equals x would become this line over here. So this is a rotation 90 degrees clockwise, and it's y equals minus x. The next type of transformation is called a reflection. And with the reflection, it depends on, in the case of a linear equation, if I'm reflecting with respect to the x-axis, then this line here is a reflection across the x-axis, so it is symmetrical with the x-axis. But if you look, it's also symmetrical with the y-axis because any point, this point here reflected across the y-axis would be this point here. So 2 comma 2 becomes minus 2 comma 2. Here we have the function y equals the absolute value of x. And the first thing I want to do is I want to do a translation where I shift this up or down. So I would take the same equation, y equals absolute value of x, and I would add 2 to it. And what I've done is this is a family of functions where this is the parent function, and I have shifted it up 2. And the same would happen if I was to do minus 4. It would shift it down 4 by subtracting 4. Let's take a look at a reflection. So now, for the reflection, I would put minus absolute value of x. And what I see is that I have a reflection across the x-axis by simply putting the minus sign in front of the absolute value of x. In order to rotate an absolute value function would involve a trig manipulation, which is the subject of a separate video, so we'll move on. Next, in our explanation of transformations, we'll look at quadratic functions, and the most basic in the family of quadratic functions would just be y equals x squared. First thing we'll do is a translation. We'll do a shift up 2 and down 4. So to do up 2, I would just add 2 to the x squared, and I've shifted the entire second degree function up 2 spaces. And if I was to do minus 4, I've shifted it down. Now, unlike linear equations, when you shift up or down, it can also be interpreted that you're shifting left or right. So that would just entail putting a plus 1 or minus 4. With quadratic functions, the shift left or right is to put the x in parentheses. If I put a plus 1 here, it actually has the opposite effect. You would think that plus 1 would go plus 1 on the x, but it actually has the opposite effect. It actually moves back 1 space. So I'm going to put a 1 over here, and we see that the new function in this compared to the parent function shifts to the left one. And same thing, I'll leave that one there and I'll just put another one in. And this time I'll put -1 and we see that it shifted. The -1 went to the right. So when I add something to x inside the parentheses, it shifts to the left. And if I subtract something in the parentheses, it shifts to the right. And then, of course, we have combinations. I can go +4, and this will shift it. This will shift. The -1 went to the right one space, and the +4 outside shifted it up. And if I was to do -4, it would shift it down 4 spaces. So now, in order to do a reflection of a quadratic function, all I do is I change the sign in front of the x over here, and if I put a minus sign there, the parent function is y equals x squared, and the reflection with respect to the x-axis is y equals minus x squared, and they are symmetrical about the x-axis. Now, the same thing can happen here. I can shift this to the left or right. I can come up to, I'm talking about y equals minus x squared. If I was to add 5, I've shifted the parabolic function up 5 spaces. And if I was to subtract 2, it would shift it down 2 spaces. So what I did here was, first, it's a reflection. The parent function is y equals x squared. The minus sign made it reflect across the x-axis. The -2 shifted it to the right 2, and the -2 outside the parentheses shifted it down 2. Rotating a quadratic function would also involve trigonometry, which is the subject of a separate video. But you can do this manually by going with selected points and graphing them to get an approximate graph. But understand that if I actually rotated this 90 degrees and I had a graph over here that went like this, I wouldn't have a function because it would fail the vertical line test. We've done a reflection across the x-axis, and we saw that the graph went upside down over here. But think about this for a second. If I was to reflect across the y-axis, flipping these 2 points left to right, what I would get is the exact same graph. And here's why. Starting with y equals x squared, if I was to change the y equals f of x, so we'll put f of x equals x squared. And then what I'm going to do is I'm going to change this. I'm going to flip the x's with the minus x's. So I would have x of minus x equals minus x squared. When I square the minus, I'm just going to get the same thing. So f of minus x is going to again equal x squared. So it's the exact same graph. The next area for us to explore are stretches and shrinks. Well, stretches relative to the y-axis or stretches relative to the x-axis. We're going to notice that a stretch on one actually can be interpreted as a shrink on the other. So let's start off over here. My parent function is going to be y equals x squared. And what I'm going to do is I'm going to do 2x squared. And notice with the 2x squared, what I've done is, am I doing 2 times x then squaring it? Or am I doing 2 times whatever number x was being squared? Well, let's look at that. So the parent function's the green one. And let's pick a number that's on the graph. And we see that we have where x is 2, y is 4. And where x is 1, y is 1. Let's look at the x is 1, y is 1. Well, when x is 1, y is 2 on the one that I did 2 times that. So a horizontal stretch is when the parabolic function moves away from the y-axis, and that is when a is between 0 and 1. Obviously, we can't have, if we did a minus in front of there, strange things will happen. We'll take a look at that on the graph. And then a horizontal shrink, which is going to move the parabolic function closer to the y-axis, is when a is greater than 1. Now for the vertical stretch, when a is greater than 1, that stretches a point away from the x-axis. And a vertical shrink is when a is greater than 0 or less than 1. Horizontal stretches and shrinks are when I'm using parentheses around the x. Let's take a look at what happens. So for the horizontal stretch, a has to be between 0 and 1. So I'll put this one up. So the parent function is y equals x squared. When I change a to 1/2, what happens is, let's pick a point on here. So when x is 1, y is 1. Now what happens is I'm taking half of x, but it's going to be squared. So when x is 1, y is only a quarter, because when I square the 1/2, I get 1/4. A horizontal shrink is when a is greater than 1. Here I've entered a 2. So here, now when x is 1, y is 4. And looking over here, when I square 2x, 2 squared is going to be a 4. So I have when x is 1, y is 4. Next, we're going to look at a vertical stretch and a vertical shrink. A vertical stretch is when a is greater than 1, and when I put the graph in, what happens is a particular point on the graph, in this case, we'll say when x is 1, y is 1, what happens is that x point then moves away from the x-axis. And even though this is a vertical stretch, it could be interpreted as a horizontal shrink. And next up is when a is between 0 and 1, this is called a vertical shrink because a given x point moves down closer to the x-axis. So the vertical shrink could be interpreted as a horizontal stretch. And the difference for the vertical stretches and shrinks is that there's no parentheses. And what you're doing is you're squaring the x and then taking half of it. And over here, you're squaring the x and then multiplying by 2. Here we've gone back to a linear equation. I have y equals x. And what I want to do is the horizontal shrink first. So the horizontal shrink is when we have the parentheses and I'm multiplying the x times 2. And when I do this, the horizontal shrink pulls the graph toward the y-axis. Notice that on the original equation, we had when x is 1, y was 1. Now when we have x is 1, y is 2. And it's pulled the line toward the y-axis. Now let me turn that one off, and let's turn on the vertical stretch. Well, the vertical stretch means that I'm increasing the x this time by a factor of 2, so I have no parentheses here, but notice that this is the exact same graph. And that's because on a linear equation, the horizontal shrink and the vertical stretch are the exact same thing. When we look at a vertical shrink and a horizontal stretch, well, the horizontal stretch is when we have parentheses and the a is between 0 and 1. I turn this one on, you'll see that the horizontal stretch pushes the line away from the y-axis. And now when we go to the vertical shrink, which has a being multiplied by x, we notice that it's the exact same graph. So on linear equations, a horizontal shrink is the same as a vertical stretch, and a horizontal stretch is the same as a vertical shrink. Without using a graph, let's transform a quadratic function. The given function, it says here, is f of x equals x squared minus 5x. And then what we're asked to do is let the graph of g be a translation 3 units to the right and 2 units up, followed by a reflection in the y-axis of this graph. So what I'm going to do is first I'll move this 3 units to the right and 2 units up, and then after that I'll reflect it. So what we're going to do here is we'll call this h of x. And what we're doing is we're going to change the x. In order to go 3 units to the right, I'm going to subtract 3 from x. So I have x minus 3 squared minus 5 times x minus 3. And then this entire thing, it says move 2 units up, so I'm just going to add 2. So first I'll simplify this first part over here, and I'll expand this. So x minus 3 squared is x squared minus 6x plus 9. And then I'll distribute the minus 5. And then I'll bring down the plus 2. Now simplifying, I have x squared, then I have minus 6x minus 5x is minus 11x. Then I have plus 9 plus 15 plus 2 is plus 26. So the first part is done, and then what it wants us to do is reflect this across the y-axis. So in the new function, what we'll do is we'll call it g of x. And g of x is simply going to be h of x with negative x's. I'm going to replace all of the x values with their opposite. So I'm going to have h of minus x. So reflecting this, I'm simply changing the x values to their opposite. So I've replaced x with minus x. And then when I actually multiply minus x times itself, I'm simply going to get x squared again. And this is minus 11 times minus x, so it becomes plus 11x. And nothing changes here because it's a constant. So this would be our g of x. So let's take a look at this on the graph. So I have the original parent function is going to be x squared minus 5x. We see that here. I'm going to pick this one point over here so that we can see if it's moving the right way. And then the next one was supposed to be 3 units to the right and 2 units up. So 3 units to the right, each box is 1. So 1, 2, 3. That's correct. And then I went up 2 units, 1, 2. It's a little below, and still. So that's correct. So the next part was to reflect the new graph across the y-axis. So looking at this, if this is plus 5.5, the new graph for this point should be minus 5.5. And we see that that is true. We have minus 5.5. So y equals x squared reflected across the y-axis, since it has symmetry across the y, would still be the same graph. But since this one does not have symmetry with respect to the y-axis, each point would be reflected to the other side of the y-axis.